lines were the Bell telephone. So whenever you have another tape and want to go.
We're all ready.
Oh, you're ready, I see. Well, when I tell you a story like I just did about a dropped piece of solder, why, you may wonder just, well, did we have any control over how the soldering was done? Well, that was just as carefully approached and considered, of course, as all of the things about how the engineers would design and not do different designs for the same thing in different parts of the instrument. So everybody abided by certain standards. The thing is that we didn't expect those engineers to spend their time soldering. And so the engineers that did do soldering were ones who were devoted to just making the first circuit of some type, the first counter or the first some other unit, which we would then have other people make many of. And so as soon as we'd gotten standardized for a first counter that we wanted many of, and over 200 of them in that case, because there were 10 digits in each accumulator and 20 accumulators, and we wanted some spares. So what we did was to hire some housewives or girls who were available, much easier to get than the men, because they weren't subject to the same kind of draft, and we didn't have to argue over deferments. And so these girls would come for a wage which was considered acceptable to the university. I don't know what it was. And we would teach them a little bit about how to solder and how to not put too much solder on, and how to not have cold joints and all the other things which are errors you have to keep away from. And having taught them, well, we had a short assembly line, you might say, which was putting together things which were in quantity, like over 200 of these counting units. Some other units were in smaller quantity, but still one could say, we've got so and so many to make of them. And so we'll set out a design. And so an insurance man actually, from Jeffersonville, I believe, outside the city here, he was also interested in, I think, radio amateur work or something. And so he became our model maker in the sense of wiring up circuits with very nice directions in which the wires would go from one terminal to another, so that they were nicely organized, not only from the point of view of beauty, which was nice enough, but from the point of view of not having the wires too close to each other when they shouldn't be, so that some circuits would not interact if they shouldn't, and so on. Well, Seth Parker, whatever his name was, Parker anyway. Clem Parker, that's right, yes. Clem Parker came in and did this kind of model wiring, and then the girls would imitate what he'd done. You see, they'd try to make their models, what they turned out, exactly like the model he'd produced. Well, that took care of a lot of the electronics, you might say, within the plug-in chassis, as they were called. Each unit of the machine, in the sense of a large panel, was itself composed of many sockets into which smaller units plugged, so that you could take those units out and test them and put an equivalent unit back in which had already been tested, and you knew that it was an okay unit. And that simplified, of course, some of the problems of keeping the machine working. But all in all, somehow the signals and the electricity had to get from one panel to another, as well as be distributed within a panel to the various plug-in units. And from one panel to another required rather large cables, perhaps 2 inches in diameter or more, with many wires in it. And these things would went behind the machine. That is, behind from our point of view. Front was the inside of the room, and the back of all these panels was toward the wall of the room. So this was a kind of a shell inside the room. The operators were inside of that, looking at the front panels, the inside of the room, and a serviceman would quite often have to go behind the scenes, as it were, between the wall and the back of these panels. And when he opened up one of these panels, he could take out plug-in units, put in plug-in units, and do those things. But somehow the circuits had to be connected from panel to panel, and this was done by these big cables, which were the exclusive job of some very skilled people whom we were fortunate enough to acquire from the Bell Telephone Company. The telephone men were short of work, you might say, during the wartime, because they were on hand. They were experts in installing new equipment, and there wasn't much new telephone equipment available to just the ordinary city service. I guess there was an awful lot of new telephone equipment that had been put into the Pentagon, and so the telephone men had enough time available so that they were glad to work part-time or whatever is available each week to construct these large pieces of cable fastened together in bundles, identified in such a way that they could be correctly connected at each panel. And then they did the process that was called ringing out, namely testing the wires so that they knew exactly where each wire went, that the place that it was supposed to go, the beginning of the wire and the end of the wire, connected to the right things when the machine was finally put together. And with the skill that those fellows had, why, our job was immensely helped, because just as in telephone exchanges, the wires have to go to the right places, otherwise you're going to get wrong numbers or faulty operation of many sorts. So they knew how to do that, and once we had found that they were available, put them on that job, we could more or less relax. They knew how to carry on under those conditions. And so we had the help that we needed all along the way there. We had found the engineers to help the design. We had found some other people to build test instruments. We had found girls who could do the soldering and wiring, and Mr. Parker who could do the original making of a model so that the girls could follow it. We had the telephone men working for us, and all of the interconnections, the cabling or harnessing work as they called it. And we had a lot of problems. It would have been a lot worse if we hadn't had those people available. One of the things that we avoided in building the ENIAC was what's called the input-output problem. That is, we had ideas as to how the numbers which went into the machine might be fed in and how they might be read out or fed out. And if we'd had time enough and enough people, we could have designed things which would accomplish that. I think we already had thought that the ideal thing, best thing we knew of, would be this newfangled stuff called magnetic tape. Possibly magnetic wire, but under some way of magnetic recording could be used to get information, numerical quantities, into the machine and get it out. But there were two things we knew about that which governed our decision. One thing we knew was that anything like that would require a lot of mechanical design as well as electrical. And we didn't have the people really on hand for that. And secondly, we knew that the Aberdeen laboratories for the ballistic research and so on were already very well acquainted with the use of punch card machines, and they use punch card machines down there for lots of different things. And so for their convenience, one should put this material in the form of punch card data when it came out, and they could produce punch card data for us if they wanted something to go in. And all that equipment was available, already been designed, already worked, and so on. The IBM people had supplied this to Aberdeen as well as many other places, and so all we had to do was to get that kind of equipment connected to the ENIAC, and we would solve a problem which would otherwise be very time-consuming and maybe delay things quite a lot. So, one of the things that had to be done was to get Dr. Goldstein to somehow make arrangements through whatever channels he knew to not only arrange the other visits that we'd had with RCA and so forth about electronic technology, but he also had to arrange that a channel was set up so that a card reader and a card punch suitable for our purposes could be procured from IBM company, and in time to match the completion that we expected for the rest of the equipment. Well, that pretty well matched. We went up and saw the IBM people, and we talked about the requirements, and they said they could help and they could meet them and so forth. And they designated certain machines to be modified in certain ways so that they would tie in with our equipment. And with plug-in cables, something like the ones I talked about, the function tables, the great big thing which already was standard in some IBM equipment, summary reproducers and things they call them, I think, so that you could get a card punch to connect with a tabulator, for instance, and punch out what was being added and printed on the tabulator. Well, with one of those big cables, which had wires for every one of the 80 columns in the card and some extra wires for other controls, with one of those machines and its cable, we could connect one of these IBM card punches to the ENIAC. All we had to do was get the matching socket and wire it up into the electronics, and the same goes for the card reader, that we could get a cable like that and plug it in, and it would go into the circuits of the ENIAC. We had a little problem when the time came that this machine was delivered and didn't seem to work like it should, but it turned out that a mismatch, a mix-up had occurred in the factory, and they'd used one set of blueprints made for one machine and applied it to a different machine, and Harry Husky and I spent our hours on the floor of the room that time with our circuit testers, figuring out what had happened and comparing it with the drawings, and finally getting everything straightened out and rectified. So it worked in the time that was required for the rest of the machine to work. And so we really had no big problems there. But as I've sort of indicated, why almost anything you touch upon, why there were some problems, it's just none of them were nearly as bad as they might have been. One of the problems we had was in the interests of reliability, everybody knows that vacuum tubes burn out. And what you'd like to do is to minimize that possibility. So you'd like to use those vacuum tubes at lower voltages than the ones that the tube companies give as their proper ratings. They don't care if some tubes burn out in use. They sell more tubes. But we thought that a failed tube would cause us more problems than it would cause somebody in his radio. And it would shut down the whole system sometimes. And, as the design grew, of course, we saw that the number of tubes was a lot more than 5,000 or 6,000. It got above 10,000, and pretty soon it got up to about 18,000 vacuum tubes altogether. Now, one of the requirements that Eckert had laid down for helping in the reliability considerations was that we should use only vacuum tubes that were in high manufacture. That is, that there were large numbers of them manufactured every year, and not some tricky tubes which were only bought occasionally and so on. The ones that are manufactured constantly, frequently, and high demand were likely to be more reliable from our point of view. That doesn't mean they worked always the same way, had exactly the same characteristics, but that from month to month and maybe through the years, the tests on them would probably give about the same results, and we could believe that the manufacturing processes, being in constant use, would probably be more stable, things of that sort. So all we wanted to know then from the tube manufacturers, such as RCA, was we are planning to use these things at a reduced voltage, and we'd like to know how much longer they will last as a result. We'd like to know anything you can tell us about the increase, the improvement in the lifetime of these tubes under reduced requirements as to how hot they have to burn or what voltages they had to withstand, and that in turn means other things inside of a vacuum tube, such as how much bombardment the plate of the tube gets, and so on. So that was a simple question. Was there a simple answer? No, no, no. The vacuum tube companies, RCA and others, had, through the years, advertised, were very proud of the fact that if you used over voltages and put more energy into these tubes, that they would give you more output. That was particularly anxious to advertise that to radio amateurs, that perhaps with a 25L6, which is one of the tapes we used, if you turned one upside down in a can of water, you might get 10 or 20 or 100 times as much radio signal out to reach the other end of the world in an amateur transmission. He could set some records for distance and all that, but nobody apparently had ever tried to collect any figures as to how long a tube would last if you sort of put it on a diet and said you can't have any more than the amount of electricity necessary to just barely operate you. And so the real question was, at what point could we reduce the heat of the tubes and the plate voltages and other things and still get adequate operation out of them? Nobody could tell us how long it'd last if we did that. And so we made our tests on that basis, that we found that we thought that with all of the reliability specs that we'd set up and what we wanted to do, we could get the signals we wanted and have the engineers all abide to it by operating things at half the plate voltages and reducing the heater currents from 6.3 volts down to maybe 6.05, or I've forgotten exactly the figure, but anyway, we chose a figure. But to have a hedge there, why every part of the ENIAC was supplied by transformers in which there were adjustable contact taps, as they call them, so that if the choice we'd made for the heater voltage turned out not to be the best choice, that we could vary it without having to throw everything out. We didn't have to buy new transformers. Transformers cost a little more if they're made with taps, but that was good insurance too. Well, later tests proved that apparently we'd hit it just about right. That is, there wasn't any need for either increasing or decreasing the voltage on the heaters, and the tubes did last a considerable time longer. And the way they finally expressed it was, of course, that the mean time between failures, how long can you expect to run before something happens to mess up everything, stop your calculations, and so on. Well, when you have 18,000 tubes, you see any one of those tubes might go out. Why, the mean time between failures could be awfully short. And as we progressed in building this thing, a few other people got to hear about what we were trying to do, and including people like Nobel Prize winner Enrico Fermi. And he, listening to some of the Los Alamos people who were being asked by von Neumann to come up and put a problem on the ENIAC to test it out, was very gloomy about all this. He said, well, now that you tell me they've got that many tubes in it and what they're trying to do and so forth, oh, they're going to have failures, so frequently, I don't know, once a second or what. He says, they will never get through fixing this machine in time to use it. It's just impossible. Well, we had thought that it would be otherwise, and we'd gone ahead with all these designs on the basis that we would have a little time between failures to actually use it. And it turned out that the mean time between failures was on the order of hours. And nobody can say exactly what, but out of a lot of figures that were collected afterwards in the 10 years that they operated that machine, why, they had quite a lot of history of that. And the general theory that we'd operated on, though, and the optimism which we had, you might say, and starting out on this and keeping on with it, was that if we could compute something like 1,000 times faster, and the machine broke down, say, once a day, then it was all going to be worthwhile, because nobody had anything that could compute that fast, and problems which needed that kind of speed just couldn't be done at that time. They were ignored and bypassed as essentially called impossible problems. And so if you could assemble 1,000 men during the war to work for a year on something, and here this machine might, with just a small staff of a couple people, be maintained so that that problem could be done in 1,000th the time, why, it'd probably mean that we'd get useful problems done, and problems that would not have been tackled before. That's, of course, turned out to be the case. History, I think, shows that the ENIAC, as its first example of what could be done with electronic computing on a large scale, already justified itself that way. Nowadays, of course, well, we've got computers that do 1,000 times faster again with no trouble at all, and work on much larger problems because they can store many more numbers and don't have to rely on the rather slower mechanical card punch machines which we use to get numbers in and out. We figured that this was pretty well suited for the problem of computing firing tables. I think Aberdeen agreed with us. We had a pretty good idea as to how we would set it up for that, and it was demonstrated when we finally finished the machine, and that it could be set up that way, and it did do these things which we had postulated in advance, anticipated that we would be able to compute the path of an artillery shell in perhaps less than a minute or so. The shell itself would take longer than a minute in the air to find its target. you might consider the shell a kind of analog computer, you see, checking out what this digital computer would predict for it in a firing table. And compare that with the fact, of course, that the same trajectory on the differential analyzer might take 20 minutes, and it might take a couple weeks for a girl to do it. So we were meeting our expectations with respect to the speed advantage, and we thought we had other advantages as well. The one advantage that we did not try to worry about, is something that we could have worried more about, was how do you set it up to do a problem. And as reported in the very first 6 months project report, which we wrote and delivered to Aberdeen, at December 1943, we started in June, theoretically, that was the formal date the contract began. So there in December, when we wrote that report, we explained that although other methods of setting up and seeing that the machine operated in accordance with whatever the particular equations required, whatever it was trying to solve required a certain sequence of operations. Well, how do you get that sequence? One way would be to have some rather complicated gadgets which would make an automatic setup. We said that was too complicated at that time, and it was better for us to spend our time on other things, because the anticipated first use of this machine was to try to do these firing tables. And it was expected that you would set the machine up once for a particular gun. You just don't compute one trajectory, you compute all the trajectories you might need to make a whole book of tables, which the gunnery officer then uses by interpolation to say exactly which way he points the gun and what charge he uses and so on. So we said, if you're going to spend 2 or 3 weeks just working out variations of this with different gun elevations and different muzzle velocities and all the other variables, and different density and temperature of the air, for instance, the shell had to go through, and that, incidentally, for these big shells, they go up miles into the atmosphere. So the density is not inconsequential in its variation. Why, you take into account this drag function that they, in the upper air, the artillery shell has less resistance to its motion, loses its speed more slowly, and so on. With all of these variables set up, then you work out all the variations that you wish to get this firing table. And so the same setup might be used a week or 2 weeks or 3 weeks before you've got everything you wanted to know out of that particular setup. Or perhaps you might, within that time, have just changed a few parameters on a function table or something to see what effect that would have on things, and so on. There are lots of possibilities where the anticipated use would be that you kept the same setup for a long period of time, and the girls or whoever was setting up the problem would only have to plug in wires and turn switches for maybe a couple hours. Might even take them a couple hours more for somebody to go through and check that they really had done everything it did. You might call it proofreading, or checking the settings on the whole machine. But whatever you did, this was a small time in comparison with the total amount of calculation you're going to do on that particular job. Then you change over to another job and you start over. But again, the setup would be small. Whereas we were really trying to beat the schedule, help win the war. We were doing this all during wartime. We hoped that we would finish the machine in time, that it would be useful just for the war, if to forget about the possible future uses in peace. Well, we didn't quite make that. the war was winding up, when we were beginning to wind up making our machine complete and testing it. But we still felt, as I say, that it would have taken us much longer to have worked out a different method of doing the programming. One of the methods, which was sort of obvious, we thought, was, of course, to store some of this information in various, whether it be switch settings or internal to the machine, and ring counters or what. In fact, there was a whole storage, you might say, of what the computer was doing in its program, built into something called the master programmer. A set of 2 panels which could count how many times you had done a certain operation and then switch to a different operation. For instance, it could also say, this operation should continue until a certain number goes negative. This was a branching operation in modern day parlance, that it tested and branched. That this essential line of program would be continued until a certain negative condition prevailed in a number, and then you'd do a different program. The simplest example of that, of course, was when you're computing a firing table. One of the numbers at interest is what's the altitude of the shell. When the altitude of the shell comes back to ground level, if supposing you're firing in the upper atmosphere to begin with, when it comes back to ground level, or 2,000 feet below ground if you're firing into a valley or something, there's a point at which you say, that's enough of that. So what you want to do next? Well, you want to print out another number, you see. So you've been every so often counting and printing out every 100th time that you step-by-step integrated, and now you've reached the end of that path, and you print out the final result for that, and you branch, and you go and get from the card reader another elevation of the gun or another something, another parameter, and you start another firing table going, see, and so it goes. Well, you might say it's a perfectly good way to look at it, that function table, in doing those things, was an electronically varied part of the program. It was counting, and it had to do these things at electronic speeds because some of the things that it had to respond to had to respond quickly, otherwise it would delay the whole operation. We had to see that the operation was not delayed by any part of the total chain of operations necessary to do a calculation. So it's all very well to say that you will decide after you look at the numbers as to what you're going to do next, and that was in effect the fault of this machine that Atanasoff had projected, in which I went out to Iowa to see in 1940. That he had to stop and punch more buttons on the machine for every little operation he did. It was not only special purpose, but it was limited to human speeds. Well, in this case, we then saw to it that vacuum tube and electronic speeds were available wherever necessary to make the decisions as to what comes next in the program, so as not to hold up the electronic speeds of multiplication and addition and so on. But beyond that, why, the major sequences of what happens first and what happens second and so forth, and how those things are chained together, so to speak, so that the computation goes as planned, was done with what we call patch cords sometimes, wires which ran from place to place, and when one accumulator was through adding something and had its number ready to feed to the multiplier, say, well, it sent a signal over to the multiplier and says, I've got a number for you, essentially. And it didn't use those words, it merely sent a little pulse along a wire which the programmer, the girls who set this thing up, they would put this wire in a socket which would stimulate the multiplier to start taking that number and multiplying whatever it should. And there'd be other wires, of course, that fed the other factor and so on. Well, all of this communication from unit to unit in the machine seemed a little cumbersome, and I've heard people talk about it as if it was just terribly cumbersome, of course, because the patch cords were big, and the trays in which the signals for the digits from one machine to another, 10-digit numbers and a sign, or 11 wires that had to be conducted from one machine to another, just to tell it what that particular number was that it was now sending. Those trays that carried those numbers were fairly heavy, but they didn't have to be moved much. But when they did have to be moved, they were flexible enough to be placed where they were most needed. Why, it was a little bit of physical labor to do it. So from some aspects it looked like a very cumbersome machine, but it was a very flexible machine. And among other things, it was a very parallel machine. Now, I've seen claims that other machines were the first parallel machine to be built. Several such claims for different machines. But I don't know that anything was more parallel than the ENIAC, which was the first machine. The digits were sent, the 10 digits of a number were sent simultaneously from one unit to another unit. Different units could be operating at the same time. The modularity was such that you could be performing one task, addition, subtraction, or something with one part of the machine, and at the same time doing a multiplication over here and a division over there, and maybe 2 or 3 other additions. And simultaneous with all that, you could be taking in to a storage the numbers which you're going to use in the next calculation and feeding out the results of the calculation that preceded the one you're now doing. This is simultaneous buffering, as people sometimes call it, of input and output. So you have 3 things for certain going on at once. Input being readied for a calculation to come. Calculations of the present sort being run, and then the results of a previous calculation being put out into punch cards, in this case, and output. Years later, some big computer companies hailed that as being a big new advance in the construction of their electronic computers. Simultaneous input and output buffered with the calculation. It was in the very first machine. Well, all these things we thought were obvious things to do because didn't take much thought to think of how nice it would be, and all we had to do was decide, is it a hard thing to do or an easy thing to do? And we decided that in view of what we were trying to do, the speed with which we were trying to realize in these calculations, that it was worthwhile having this buffering so as not to slow the whole electronic stuff down to the speed at which a card machine could punch out the results, for instance. Otherwise, you might have 5 minutes of calculation, go ahead and then wait 3 minutes for something to get punched into cards, maybe, or something. That kind of a contrast could occur, and we didn't want that. So we did this. We also, I guess, were one of the first to build an interlock into a machine, so that when different conditions which were running in parallel took different times to be finished, and both things had to be finished before the next calculation could occur, that what we call an interlock circuit would be set up so that both things had to be finished before the next calculation could go ahead. It might take longer to take a square root, for instance, of some number. Simultaneously, the multiplier might be multiplying something, yet maybe the next step in the operation would be to take the product from the multiplier and the square root from the square rooting module and, say, multiply them together or add them together or divide them or whatever. But you can't do that until both results are ready. And nobody knows just how long it's going to take to do that square root. Depends on the number. And whether the digits are large or small and how many of them there are. And to some extent that occurs, of course, in the multiplication process too, that multiplications vary in time depending on the factors that you're multiplying. So you set up some interlocks. We had a number of interlocks that could be plugged in and used that way for different processes. So there were a number of features there which are such that you can almost say there isn't anything new under the sun after the ENIAC, that we had them somewhere. And some of them have been forgotten about, but they're all, if we thought they could be used to advantage and didn't cost too much, well, we used them. Now I used that phrase, and don't cost too much, which is the key then to why we did the programming sequencing of the operations the way we did by these patch cords. And just put a certain amount of electronics into the master programmer which could count operations and branch on negatives and things of that sort. We just couldn't believe that in view of the cost that we were devoting to this storage of numbers, like 10-digit number and the controls of that 10-digit number in one accumulator, we had 500 tubes in the panel that did that. I mean, it sounded like a lot, and it was a lot. But it had a lot to do, because it isn't just storage. We were using a reliable method of storage, the best we knew at the time, but much improved on nowadays, of course. We had a reliable method of storage, but not necessarily an efficient one from how many tubes it used. These 10 digits, why, a counter could be made with only 4 vacuum tubes instead of the 10 that we used for our 10-digit decimals. RCA was making their counters with 4. And they just said, well, we'll count on a base 2 system, you see, and 2, 4, 8. And how do you get above 8? Well, you have to have some other digit somewhere. So essentially what they did was make it capable of counting to 16. 4 tubes, the 4th power 2. But then they sort of short-circuited the operation of that counter, so that when it got to 10, it set itself back to 0 instead of going on to 16. So with 4 tubes, they had a decimal counter, which some people wanted for their chronographs and so on. What we avoided, as we say, in the research for the development of this first one was that business of trying to develop and build something which would automatically convert from binary system to decimal system. We built it so it would be decimal from the outset, you might say, in using these decimal counters. And that made it easier for us, though, you see, to feed numbers back into the punch card machines, which were already punched in a decimal system, and to read numbers off such machines. So altogether, why, as engineering always should be, it was a bunch of compromises, a bunch of trade-offs as to what was the best way of doing this for now. And all the ideas that we had about other ways of doing it, for a long while, we just sort of pushed them off. We said, okay, that's a good idea, but wait. We'll do that later, maybe. Right now, we got to get this machine done, and we can't get it done by changing designs and incorporating every new idea. So we pushed on, and it was in December 45 when we began to think that we were close to the end, because it was then that the people from Los Alamos, Nick Metropolis and Stan Frankel, were up there to try to put on a problem from the atomic energy laboratories, a classified problem that nobody could discuss. We didn't know what it was about, but for some time, why, they worked with the business of how to set this thing up and what was available to them. And the machine did the job that they wanted it to do, and we didn't even know then what it was doing. Years later, before we found it had something to do with the possibilities of building a hydrogen bomb, a fusion bomb. But at any rate, that testing then went on into the next year, 1946, where we had a lot of things we wanted to try. And part of the machine wasn't completed exactly as we'd originally scheduled, but I can't remember now just when and how that was. But Xuan Chu and some others of the engineers there, along with Arthur Burks, I think, worked a while on trying to get the divider and square rooter to its final perfection, you might say, through its test. But practically everything was working well when it was demonstrated in February 46. And so the word had been sent out before that, the Army Ordnance, to come and prepare for whatever they wanted to do in the way of press releases and publicity. And they chose to say a lot about the existence of the machine and how wonderful it was, of course, that Army Ordnance had such a thing. They'd been pioneers in backing this, and now they were about to reap the fruits of it, actually. No one else had anything equivalent. So there was a press conference at which all of us present at the scene at that time that they thought ought to be at a press conference. Dr. Goldstein from Army Ordnance and Dr. My mind went blank just then. Dr. Brainerd of the administrative staff of the Moore School, and myself and Press Eckert and perhaps a few others were told to be ready to say a few words to the press, because this is a new concept. They won't even realize whether it's important or not, unless we try to tell them that it really means something. What's it good for? And so we prepared these things and we distributed them in press release packets, and something like January 15th, or was it February 1st? It was a few weeks before the big function was to occur, where the press came and we told them how important this was for not only the Army, but for the whole world. And I tried to bring it home a little bit, I think, by saying that this may even make the price of bread a little lower, because it may do something to help in either the farming and the growing of wheat, or in the baking of the bread, or something, or it might reduce our taxes, which would indirectly affect their hidden taxes in bread and so forth. But all kinds of things we thought about that would be possible effects of this computer. And of course, much later we realized one of the things that never entered our mind, and we did not mention at those press conferences, was the possibility of spaceflight. Werner von Braun, who just recently died, was credited with the statement that we couldn't have gotten to the moon, we couldn't have made a lot of these space flights without the characteristics of the computer to, in real time, control what was going on out there with that vehicle and control the jets and so on, so that everything worked the way it was wanted. But at that time, I'd heard of Goddard, I'd heard of rockets, I've heard of a lot of things, but the whole space age somehow did not unfold in my imagination then as something which was going to be keyed to the use of computers, which it obviously was. And just impossible for them to have done what they have done in any way without having computations to first tell them what was possible and what they could do, and then control things so that they could do it. Well, we talked about design of airplanes by computers, for instance. Perhaps the elimination of wind tunnels, that the aerodynamics could be predicted by computer, and so on and so on. But that one blind spot, we just didn't think of the space age. Want to rest?
Take a little break right now so you don't have